Bon, alors, it's a pleasure to introduce Martin Pinsonnault, who is going to give the last talk of this workshop on the embeddings of symplectic balls and configuration spaces. Martin.
So first, I would like to apologize for three things. First, because my voice may disappear at some point. And second thing, because I was not able to attend the previous talks. And third, because I was forced to use slides instead of writing everything on the board. So beside that, I hope to be able to explain a few things. Okay, so okay. Okay, oops. Okay, so here's the outline. I will very briefly go through about 20 slides to explain a little bit of the background, why we are interested in embeddings of symplectic balls and symplectic manifolds. And I want to make the connection with complex geometry. And then most of the talk will be about what happens in the special case of rational form manifolds. So either S2 cross S2 or CP2 or a blow up of these two minimal manifolds. And I will give pretty concrete results towards the end of the second section about the embedding space for a small number of balls. And at the end, depending on how much time is left, I will go through how we get these results and what is actually the main idea, which is going through what is called an homotopy decomposition for some symplectic stabilizer. And eventually, if I still have enough time, I will even go under the hood and start looking at very precise questions that we have to solve in order to understand embedding spaces. So here's the background. So I start with a symplectic manifold dimension 2n. You all know what it is. So it's an even dimensional manifold equipped with a closed non-degenerate 2 form. What is important? Well, the closedness is equivalent to a sort of zero curvature condition that tells you that essentially there are no local invariants. And the non-degeneracy means that you can use the symplectic form to establish a duality between vectors and one forms. And in particular, it makes sense to talk about the symplectic gradient of any function. Okay, so on a closed manifold, then there is also the fact that from Stokes' theorem, we know that the symplectic form induces a cohomology class, which is on closed manifold, which is non-zero, and whose top power is the volume class. So, as I said, there are no local invariants on the symplectic manifold, so you all know the theorem. So a symplectic manifold has around any point a neighborhood that is symplectomorphic to a standard ball in the standard model, which is the even dimensional R2n. Actually, this can be extended quite a bit. So if you define a submanifold to be symplectic, if the restriction, of course, of the form is non-degenerate, then you can extend this double theorem to neighborhoods of any embedded, say, submanifold that is symplectic. So in particular, in dimension 4, if you look at a proper submanifold, so it will be a dimension 2 closed submanifold, then a neighborhood symplectically is completely characterized by the genus of this embedded surface, and then its self-intersection and its symplectic area. So another way to think about structures is, of course, to look at their automorphisms. And we say that a diffeomorphism is a symplectic homomorphism or a symplectic automorphism if it pulls back, it preserves the symplectic form. Okay, and we denote by simp the group of all those symplectic homomorphisms. Now, remember that for any function, we have a well-defined notion of a symplectic gradient. So now, if you take such a function, capital H, and you take its symplectic gradient, which is defined by this equation, the H is given by the internal product of the vector field with the symplectic form, then you can take the flow, this vector field X sub H is uniquely defined, the symplectic gradient, and then you can consider its flow because we are looking at compact manifolds, so the flow is different all time. And just using Cartan formula, you see that the Lie derivative along this flow at all time of the symplectic form is always zero. So meaning that the flow always preserves the symplectic form. So in particular, the flow of any such symplectic gradient is a symplectic transformation. Now, of course, there's plenty of functions you can consider, and this shows already that the group of symplectic homomorphism is always infinite dimensional. Actually, if you look at the subgroup generated by all these time one flows, it's not hard to show that it generates actually a subgroup of simp, which is called the Hamiltonian subgroup. And this subgroup by construction is connected, so it belongs to the connected component of the symplectic homomorphism group, which is denoted simp0. This itself is inside simp H, which is for me the notation for all symplectic homomorphisms acting trivially on homology. And this in turn is inside the full symplectic homomorphism group. And because preserving a symplectic form means that you preserve the volume, then all this sits inside volume preserving diffeomorphisms. Okay, so this is more to establish the notation than anything else. And there's this famous results of Banyaga that for say a closed manifold, Ham is a simple group because it contains flows, plenty of flows. It's very easy to see that Ham acts n-transitively on any compact manifold for all positive number n. So this means that you can always find an Hamiltonian transformation that takes n distinct points to any other collection of n distinct points. So you can realize this by Hamiltonian diffeomorphisms. And another result of Banyaga tells you that as an abstract group, if you forget the topological structure, just the group structure, so completely characterizes your manifold M. So meaning that if you have two symplectic homomorphism groups coming from two manifolds, and they are abstractly isomorphic as groups, then actually there is a diffeomorphism between the two manifolds that intertwine the symplectic structures. Okay, so that's a Banyaga result. So essentially, the group Ham contains all the information about your symplectic manifold. And now we can look at embedding spaces of various things. So here I'm only considering symplectic embeddings. I'm completely discarding, say, Lagrangian embeddings, which is another very interesting field, but which is quite different. So I take a symplectic submanifold. This manifold can have boundary, but if it has boundary, I will assume that actually M, the ambient space, oh, there is an X here, it should not be there. Anyways, some typo. But I will always assume that M has no boundary. So S is a submanifold symplectic, and I look at all possible symplectic embeddings of S into M. S may be, say, a strictly smaller dimension, or it can be even of the same dimension as M. And I will look at actually the set of images of these embeddings. So just the space of some manifolds without any parametrization. which is what I denote by a sort of a script I embedding. So the set of all images of these embeddings. And this, of course, at the level of, say, if you think of these things as infinite dimensional manifolds, then actually there's a submersion of the embedding space, which is parameterized embedding to images of embeddings. And there's a reparametrization group, which is the symplectomorphism group of the manifold S itself. And there's a proposition, well, I say that it is due to Banyaga. Actually, it follows from Banyaga work published in 78. It follows pretty directly that the group acts transitively on each part component of the images. So there's Banyaga extension theorem, which is, for instance, proved in McDuff-Salomon Bible book and so on. But actually, it's usually quoted in a weaker form than what appear in the original paper. So in the original paper, there's a stronger form of the isotopy extension theorem. And if you look at this carefully, then you see that you can deduce from this that if you forget the parametrization of an isotopy of symplectic submanifold, if you just look at the displacement of the set, then this displacement can always be realized by an Hamiltonian isotopy, as long as you know that they exist, at least a smooth symplectic displacement of your subset.
So this S is no, what's the conditions on S? So
No condition.
no condition on the complement or anything.
I'm just looking at a compact, nice, embedded submanifold.
Okay, is that all?
Yeah, I'm assuming everything is smooth here. We don't have kind of singular or self-crossings, of course, because if you have self-crossings, then of course, kind of symplectic angle is an obstruction to deforming.
But assuming like orthogonal, that's still true. Like
In dimension 4, yes.
in higher dimension, it's
There are kind of local invariants that you have to be careful with.
in dimension,
In dimension 4, that's true, and this is what we used to do when we look at more complicated configurations.
You say this actually follows from.
Yes. Yes,
I
exactly.
was trying to prove it. But
Yeah. And it appears actually, it appears in a paper by Oru on mirror symmetry at some point.
Yeah.
Yeah. And he grants Gromov actually for the idea, but actually it goes back to Banyaga.
Oh,
Yeah.
I just recall what is capital C?
Okay. So yes. So capital C is that you just pick one embedding and you look at the component of this embedding in the space of all images. So it's just the component of a specific.
No,
The component.
of a specific embedding.
Yes. Yes. Because it's only on components that this action of Ham is known to be transitive. We, of course, it cannot be transitive on different components. Okay, because Ham is connected. Okay, so the corollary to this, yes, is that there is always a vibration when you put the correct topology. There is always a vibration from, say, the connected component sim0 onto the set of images restricted to a specific component.
I'm confused. So the proposition of Banyaga, the S, what is S? Is it?
Think about just a submanifold, say an embedded curve inside a full manifold. That's essentially what we will be playing with, or a closed ball in your manifold.
Something should be maybe assumed, right? Because you can have like annulus in torus, which you kind of go around. That's going to create some flux.
It's Ham. It's really hard.
I think I gave an example of a symplectic loop that cannot be realized by.
No. But no, but because this is a Lagrangian thing. It's not a symplectic.
Symplectic, annulus. Annulus is a symplectic. Right, it's not. Maybe you want like, you know, pi1, trivial and pi1 or something.
Wait.
Something. If everything is simply connected, then there is no problem like this.
Yeah. Of course, there is the flux, and that's precisely what Banyaga actually identified as an obstruction. The relative flux of the displacement. But assume simply connected. This is anyway what I'm using. Okay, so
Assuming S or M, which one? All of it.
no. You assume simply that S is simply connected.
S
That
is
there is no flux restricted to the display induced by the displacement of S on H1. Okay, so but I know what you mean, but actually there is something here more subtle that I.
It's right. If you take just an analysis on the cylinder, you can just lift it. And this is a path in image of embedded. But there does not.
Yeah, but you have to assume something about H1. So yeah, so the point is this. For simply connected subsets, everything is fine, and so usually this extension of isotopy is stated with a condition like the relative group H2 of M relative to S must be 0. But actually, that's way too strong a condition. What you have to assume is that the image of the flux under the boundary map of the long exact sequence of the pair is 0. So this is the exact, which of course is implied by a simple connectedness. Yes. Okay, so now the non-squeezing, you all know the non-squeezing theorem of Gromov back in '85. So if you try to squish a big symplectic ball into a thin symplectic cylinder, and you look at the cross area of the two-dimensional cross section here, if this is only possible if the section of the ball has an area that is not bigger than the area of the section of the cylinder. Okay, so this is the non-squeezing theorem. But what is remarkable with the non-squeezing theorem is that it leads to immediately a sort of invariant that is completely global in nature, which is the Gromov capacity or Gromov width, which is the size of the biggest ball that you can embed into your manifold. If your manifold is compact, of course, this is bounded by some volume constraint. But even as this example gives you, even if your target manifold is not compact, this number can be finite. And what is remarkable with this notion of capacity is that it's in some sense completely characterized what it means to be symplectic. And so this is another result by Gashberg, and maybe a few others. Almost immediately after the definition of capacity. So if a diffeomorphism preserves, say, the capacity of balls or ellipsoids, if you want, then automatically you know that this diffeomorphism is either symplectic or anti-symplectic. So preserving the size of all possible embedded balls is equivalent to essentially preserving the symplectic form up to a sign. So this basically characterizes what it means to be symplectic, and that's why understanding, say, space of balls inside your manifold tells you a lot about your manifold and what you can do and what you cannot do in your manifold. And there are various there are variations on this idea, which is a packing problem. You all know this. the Gromov capacity then can be generalized by looking at more than one ball and of various sizes. For me, the size would be the capacity, which is essentially the area of this two-dimensional slice passing through the origin. So for me, C1 and Cn are not radii, they are capacities. And so you take a bunch of balls, the n of them of various capacities, and what you can do is to try to see whether they embed or not inside your manifold. So this is the packing problem. You can restrict to considering n balls of the same size, and then you can renormalize by looking at the total volume that is filled by these balls over the total volume of your manifold. So this gives you something that is always between 0 and 1, and it tells you how much of your manifold you can fill with some balls. So if you allow the capacities to be distinct, then of course you get a slightly more general problem, but the essential features are already captured if you look at all equal capacities. So these are called the packing numbers. And just a relevant example for us is this nice result due to Gromov, Polterovich, and Megdov, where they, and Biran also, where they computed these packing numbers for CP2, and we will do essentially a sort of a generalization of this. So one ball, you can fill, of course, the entire volume because a symplectic 4-ball is actually the same thing as the complement of a line in CP2. So you fill all the volume with a single ball, but with 2 balls, you can only fill half the volume and 2 equal balls and so on. So this was one of the first instances where these numbers were computed. So since then, of course, a lot of other things were done. And now another generalization or variation on the capacity, the Gromov capacity or the non-squeezing theorem is the famous symplectic camel problem, which is, so this is the Sirjet camel, but you can take any other camel too. So you consider in R2n a plane, and you just remove this plane, but you keep a little kind of tunnel so that actually, in principle, things can flow through this little hole here. What is gray is removed from the ambient space. And then the question is, of course, whether a big ball can be squeezed to pass through this needle. The answer, unfortunately for this camel, so the answer here is that this is only possible if the size of the ball in terms of capacity is not smaller, is not bigger than the size of this hole. And so this has been generalized actually also with many other examples by Trainer. And it's still an open question whether we can find a compact example. So this is essentially asking about the connectedness of the embedding space of balls. And it's still quite amazing that we don't have a single example of a compact manifold for which the embedding space is known to be disconnected, you know, when you fix a capacity. So that's the camel problem. So this brings us to space of symplectic balls. So now consider the space of all embeddings of n disjoint balls of capacity C1 to Cn inside the symplectic manifold n. And we put the infinity topology coming from the mapping space. And as I explained earlier, what we can do is also consider the space that is obtained by only looking at the images, forgetting the parametrization of the balls. And as before, this is denoted with the I, kind of script I, embedding. So the Darboux theorem tells you that whatever capacities you choose, as long as they are small enough, you know that this embedding space will be non-empty, like taking a collection of Darboux disjoint Darboux charts around any collection of endpoints. We used to think about balls like, nice round shape, but remember that simp or even ham is acting intransitively on any symplectic manifold. So actually you can distort these symplectic balls in an arbitrary complex way. And actually, let me just go back to this symplectic camel problem. So if you take a very dense collection of endpoints in your ball, you know that you can move this collection on the other side anyways. Okay. So you can, by a result of Katok, you also know it's possible to prove that you can approximate and measure any volume preserving map by symplectomorphism. But of course, you approximate this in measure, not in any C0 or C1 norm. Okay. So this means actually that you can make sure that most of the volume of this ball here, almost all the volume here minus an epsilon, it goes on the other side by Hamiltonian isotopies.
Not minus epsilon.
Huh?
It's just not, you don't need the epsilon. The whole volume.
I mean, for an arbitrary epsilon,
you have just to remove.
there will always be some open set that will not be on the other side. Yeah.
If you just remove the hypersurface.
Of course, if you take the limit, epsilon goes to 0. Yeah. But I mean, you can move all the volume on the other side, whatever the size of this hole is, on the other side. But there will be always some very bizarre, tubes, living on the other side. Okay. So, so balls. In the symplectic category, balls are very badly, can have very, very, very strange and bad shapes. Okay. And the problem now is to compute the homotopy type of this embedding space. And of course, this means in particular that this encompasses the computation of all the invariant of the previous problems. So the Gromov capacity, the packing numbers, and the symplectic camel problem. All this fits inside this more general problem of computing the homotopy type of these embedding spaces. So this is just justification of why we are interested into these things. Okay. I guess that there are no questions at this point because this is pretty much symplectic geometry 101. Okay, so what can we say in general about these embedding spaces? Well, not much. Okay. So as you can imagine, because it's already difficult to compute the Gromov width, which is just asking whether our embedding space are empty or not. In general, we have no idea how to compute these things, so we don't know what the embedding space of a general manifold is. We don't even know how to address this question in general. So there are still a few things we can say in general in any dimension, and I will start by these very elementary notions. So the thing is, instead of looking at only one embedding space for a fixed capacity, of course, you can take the union of all these embedding spaces for all possible capacities. Taking all capacities, essentially remove all the symplectic features from this problem, because this allows you in particular to shrink balls as you wish. And because you can cover a symplectic manifold by Darboux charts, if you take two arbitrary embeddings up to rescaling, up to shrinking them, you can always make sure that you can find a path such that at each time, a small symplectic ball will be contained in at least one Darboux chart. And then if you know how to displace balls in a Darboux chart, then you can just, displace them all the way along some path and get on the, to the other side. And in some sense, you lose all the symplectic features. There's no obstructions anymore. And that's precisely what is made formal here. So if you allow all possible size, then there's a system of restriction maps between different capacities. This is a directed system, so with respect to the partial order that comes from sizes. And then you can look at the limit as the ball shrinks to points, which is the same thing as taking the homotopy limit of this directed system under reverse inclusions. And this is what is called here, this map, J sub infinity here. So when you take the limit as the sizes get to 0, not surprisingly, what you get is something that is homotopy equivalent to the space of symplectic frames over n points. Because you still remember what is the derivative of an embedding at the center. Okay. Now, if you this space maps further down to the configuration space of n points, just forgetting the frame, the symplectic frame. And what we expect essentially is that at the level of images, if you forget the parametrization, what you should recover is just the configuration space of n points. Now, there's just only one problem with this reasoning, which is the fact that if you restrict yourself to images of balls, then there are no longer restriction maps, and there is no canonical way to define a directed system. But there's an easy fix for this, and essentially this idea is right. Okay, so so what do we get from this? We are already in a situation where we can say a few things about the complexity of embedding spaces in general, at least for homotopy type, or rational homotopy type, just from this simple fact. So again, if I consider an arbitrary dimension 2n compact symplectic manifold, any number of balls. First of all, if I want, I can just decide on an ordering and a labeling of my balls, and I will assume this for the rest of the talk. So we'll always assume that C1 is not less than C2, which is not less than C3, and so. And then the first non-trivial, it's an exercise, but it's still something you have to think a little bit about. So there exist capacities such that at the level of homotopy group, when you look at the embedding space for these capacities, and you look at the induced map in homotopy onto the limit at infinity, which is the symplectic frames, well, you can always achieve surjectivity eventually. So this means that as the balls shrink, the complexity of the embedding space is getting, essentially at least as complex as the complexity of the configuration space of n points. Actually, frame configuration spaces. And the map, as I said before, so you can use this now to really prove rigorously that as you take the limit as the ball shrinks, what you get is a well-defined weak homotopy equivalence. And as I said in this remark here that you can see, in general, sorry, in general, it's not known yet. So if you get even some C0, starting from which the induced map to the limit at infinity is a weak homotopy equivalence. So we don't know if there is a sort of stabilization as the capacities shrink. And actually, we don't even know this at the pi zero level, which is very shocking. So it looks like it's a reasonable conjecture to say that on a, say at least on a compact manifold without boundary, there must be a size, a capacity, such that the space of embedding of all balls of this capacity or smaller must be connected. But even this very simple thing is not known. It's very, very shocking. And it's essentially an extension problem. So what we are missing is that although we have restricted maps, there are no canonical way to extend. There is no geometric flow, for instance, that will take the image of a small ball and make it a little bit bigger by a uniform amount. There is no uniform way to go through such a fattening of balls. And essentially what you would like to reduce this to the existence of some kind of geometric flows, you see. But it turns out that so far anything that that people have tried to write down are ill-defined PDEs and so on. So it's very bad. It's extremely bad, even from an analytical point of view. Okay. So now here's the first corollary, which is not completely obvious. So this is a generalization of an older result of Yared-Kedra. So if you start with an arbitrary compact and connected symplectic manifold, and you put an integer satisfying one of these three conditions. So depending on which manifold you are considering, then you need a different number of points. So for S2, you need at least 4 points. For something that looks like CP2, you will need at least 3 points. And for something that that is different from these examples, and also from some quaternionic examples, in general, we only need 2 points or 2 balls, if you want, to have the conclusion here. And the conclusion is that there exists a capacity C0, so which is a set of capacities, of course, such that for any smaller set of capacities, the embedding space is rationally hyperbolic. So this means essentially that it doesn't have a nice simple description. So for instance, its homotopy groups it has non-trivial rational homotopy groups in arbitrary high dimensions. Okay. So and there is a dichotomy in rational homotopy theory telling you that essentially the world is divided into the 2 families of rational spaces. There are the elliptic spaces where everything is essentially finite, and then there's the wild west, which is the family of all hyperbolic rational spaces, and all rational hyperbolic rational spaces have this very bad behavior. So if you look at the rank of their higher homotopy groups, then the rank of these actually grows exponentially. So it's very, very bad. It's very so there's a lot of topological complexity, and as you can see here, this only comes from the fact that a similar statement holds for the configuration spaces themselves. And because I have a surjection, as I said before, essentially all this complexity survives in the embedding space of balls. Okay. So that's very bad. So there is no hope to understand these spaces in any systematic way, but it means that even topologically, there is an intrinsic complexity that is unmanageable. Okay, so why do we persist? Well, because there are good examples still. Okay, so you have to be very careful when you choose your example. to work. So now, given a symplectic embedding, you all know now that you can perform what is called a symplectic blow-up. And the blow-up amounts to essentially removing the ball and collapsing the boundary along the up fibration. Now, this essentially creates a manifold that is diffeomorphic to the ordinary topological blow-up in the complex sense. And you can view this operation as actually constructing a symplectic form on the complex blow-up, starting from the information given by this symplectic form on your space and the embedding that is given to you. So it's a recipe to construct a new symplectic form on the, say, one-point complex blow-up. And by doing so, what you end up with is an exceptional divisor, which is the copy of CP n minus 1. And oops, it should be m minus 1. Sorry, I'll do this. That has actually lines inside of symplectic area precisely equal to the capacity of your starting of your embedding. Okay, so the capacity is remembered in the blow-up as the size of lines in the exceptional divisor. And then by doing so, you control essentially because you know this, you control what is the symplectic class of the new symplectic form, the topology class, which is simply the previous one minus C times the exceptional divisor. Here I'm using Poincaré duality, of course, to identify homology and cohomology. So I'm assuming here that everything is kind of has no torsion, you know, I'm working maybe. I have Poincaré duality. And the anti-canonical class is, of course, the one that is coming from C-complex geometry. And what is important for us is that any symplectomorphism on the base, of course, you cannot expect symplectomorphism on the base to survive this construction. If you think of this, though, as a surgery, then you realize that once you have an embedding of a ball, there is also, it's meaningful to talk about symplectomorphism whose restriction to the ball is acting like a UN, you know, a unitary transformation, because you just put it back to R to N. So it makes sense to talk about what is acting linearly on the ball itself. And you can always extend slightly any ball to, you make it a little bit larger, and you can talk about what it means for symplectomorphism to act UN linearly near your ball. And once you restrict yourself to these symplectomorphisms, then it's easy to see that they go through this construction, so they can be lifted to the blow-up, if you think of this as a surgery. And conversely, something that is acting UN linearly near the exceptional divisor, then can be pushed back to the blow down. Okay, so there are some subgroups of symplectomorphism that behave well with respect to symplectic blow-up. Let me just okay, so in dimension 4, things are much better behaved, because in dimension 4, not only we have blow-up, but we have blow-downs essentially, which are characterized completely numerically in terms of homological data. So first of all, we can say put a normals complex structure on a 4-dimensional manifold, and then a geomorphic curve is automatically a symplectic submanifold if this curve C is embedded and J is compatible with your symplectic form. And what is nice with the exceptional divisors that you get from this blow-up construction is that they are generic in the sense of Gromov-Witten theory. So they are extremely well behaved with respect to the theory of geomorphic curves. So which means essentially that once you know that they exist some -1 curve that is embedded, so -1 sphere embedded in your manifold, then actually it is generic in the Gromov-Witten sense. So it will persist under the formation of almost complex structures. And you can always make a neighborhood of these curves, say holomorphic with respect to a compatible J. And then you can blow them down by the Castelnuovo criterion. So you have a very well-defined notion of -1 curve, and all these curves essentially can be blown down, which is not the case in higher dimensions. Okay, so it's not necessary. First of all, in higher dimensions, the blow-up operation is not so nice because the exceptional divisors, the CPN -1 that you get, well, with respect to geomorphic structure, generically you will have no hypersurfaces. Okay, so you don't expect actually to be able to connect them with almost complex geometry in any nice way. Okay, so they are highly exceptional curves actually in the theory of geomorphic curves. So it's only in dimension 4 that we have this interplay between geomorphic curves and blow-ups. And this is essentially what we would be using. Okay. So what we are aiming for is, at least in dimension 4, we want to establish some sort of equivalence between, say, compact families of disjoint exceptional curves. And we want to think of them as compact families of disjoint balls in the blowdown. And we want to establish a sort of dictionary between exceptional spheres and embedded balls. And for instance, we can restate some of the previous problems. So for instance, asking whether they exist an embedding of a disjoint collection of n balls of some given capacity. In dimension 4, this amounts to asking for the existence of a symplectic form on the n-fold blow-up in the cohomology class, say, of omega minus C1 U1 to Cn En. So essentially, we restate this in terms of existence of embeddings are restated in terms of characterization of the symplectic cone of some blow-up manifold. Okay, so that's the strategy. And of course, this is way too general to be done with all possible four manifolds. So we have to restrict even further. But before I restrict to smaller classes of manifold, let me just make a very, very quick comparison with the complex blow-up that you all know. In complex category, so as long as only the smooth underlying manifolds are involved, the complex blow-up gives you exactly the same thing as the symplectic blow-up. We already mentioned that. In dimension 4, as I said before, you can always contract -1 holomorphic spheres, embedded holomorphic spheres, which is the Castelnuovo Enrique criterion. And there is a big difference between the symplectic and the complex category, which is the last two bullets here. So in the complex blow-up, so if you blow up, say, a collection of endpoints, disjoint points, and you look at what is the result as a complex manifold, and you compare this with the blow-up of another collection of endpoints. So it's a very natural question to ask, okay, when are these two complex manifolds the same, or biholomorphic? And it turns out that this depends in a very, very subtle way on all the possible complex curves passing through your collection of points. And of course, taking an arbitrary collection endpoints here, another arbitrary connection, I don't expect the set of curves passing through these points to be the same. And this is what essentially makes different create different complex structures on the same underlying smooth manifold. So and now what you want to do, if you are very ambitious and a little bit ignorant, what you want to set yourself as a problem is to try to understand, okay, what collection of endpoints give me the same blow up? And of course, a sufficient condition would be to take points that are holomorphically equivalent under the automorphism group of the base manifold, but that's too much, way too much demanding. So actually, it's a more subtle question to classify all these points leading to the same n-fold blowups. Another point also, of course, is that after you blow up once, then you can blow up on the exceptional divisor of the previous blow up. And then there is this notion of infinitely near blowups in complex category. And then if you allow these things, then the question becomes absolutely horrible. Okay, so this is a very hard question. Even if you restrict yourself to CP2, which is the nicest possible manifold, essentially what you want to understand here is all the Cremona group acts on all configuration spaces of points and so on. So it's a very tough, difficult question. Now, the symplectic side of this is that essentially in the symplectic world, the location does not matter because simp acts intransitively on any collection of points. So the location does not matter. What matters are the sizes. So you trade essentially going from one picture to the other, you trade, say, location of points and subvarieties going through these points to, say, sizes of balls. Okay, so that's a sort of duality between the two sides, which is very naive, but in some example, actually, it's an exact duality. And this is what I want to explain. So symplectic balls in rational manifold. Now we restrict ourselves to CP2 essentially, but you can think about the same things should work in some number of blowups, and the same thing also works for, say, S2 cross S2, but I will focus myself on CP2. And now I will start using some deep results. The first one, which is essential in dimension 4, which is this result by Granoff. So if you restrict to, if you look at the symplectomorphism group of a closed 4-ball, then it retracts onto the linear group U2. So this means essentially that there are no complexity coming from, say, local considerations in terms of symplectomorphism. The second thing that is crucial for us, which is actually dependent on this lemma, is something that François and I put a long time ago, which is the fact that when you look at, say, n balls, and you look at the action of the symplectomorphism group on this collection of m balls, if you assume, for instance, that you look at one component in which the action is transitive, then there's a sequence of homotopy equivalences here. And what is important here is that here, if you look at the symplectomorphism group, that sends the collection of balls onto itself. But remember that it's an ordered collection. So each ball is sent to itself. And I'm not permuting balls, okay, which is forced if, for instance, all the capacities are distinct. Okay, anyway. So if you look at the stabilizer of your collection, then this is weakly homotopy equivalent to actually the ones that act linearly near your ball. And because of this, you can blow up, and what you get is something that acts linearly near the exceptional divisors that come from the blow up. And again, you can show that this will be weakly homotopy equivalent to the symplectomorphism group of the blow up, sending each exceptional divisor to itself. Okay, so all these things are weak homotopy equivalences. And then what comes from this is that if you assume now that everything is connected, so I don't have to keep here the notation about one connected component. I assume that this space is connected, so I have simp acting on this, or simp zero even, then actually the stabilizer of a collection of ball can be replaced by the stabilizer of a collection of exceptional divisors on the blow-up. Okay. And then what happens here? So now restricting to rational form manifolds, there's a lot of deep results that I will very quickly recall, sorry. First of all, on the rational form manifold, so blow up of CP2 or S2 cross S2, essentially, any two cohomologous symplectic forms are diffeomorphic. That's absolutely essential result that we will make use all the time. So this is due to Danon, McDuff, Lee and Yu, and then from Lee and Lee. So there's a characterization of the symplectic cone of these manifolds in terms of embedded -1 spheres. Essentially, a cohomology class belongs to the symplectic cone of the manifold if and only if it has positive volume and it pairs strictly positively with all possible symplectic -1 sphere. Okay, so that's in a nutshell the statement here. So it gives you a numerical condition as long as you know what is the set of exceptional curves that can exist. It gives you a way to test whether a collection of ball embed or not inside a memory. And then from McDuff, we know that actually for any sizes, as long as these embedding spaces are non-empty, well, they are path connected. And in particular, I added this to make sure that we go back to the basics here. Even for the closed balls B4 of whatever capacity, but take capacity 1, the embedding spaces of any number of balls inside B4 is also connected, which is again a statement about the non-existence of complications from local considerations. Okay, so should be good. Okay, so any questions so far? No. Pretty. Okay, so now how we will investigate embedding spaces. Now we want to take advantage of everything that is known about rational manifolds. And what we will do is that actually we will look at another fibration that is closely related to the original motor vibration. So remember that if you take, the space of the symplectic forms cohomologous to one given form, you take a component here, and you take a path inside this component. Well, a path of cohomologous form, comes from actually an isotopy from Moser theory. So essentially, it means that forget about this kind of relative version. So it means essentially that diff0, the connected component of diff, always acts transitively on path components of cohomologous forms. Okay, so and this is a very nice vibration because it has local section. This section has local sections. And now we essentially state a relative version of this. So now what we do is that we consider the blow up at some number of points or balls, if you prefer. We have a collection, a fixed collection of exceptional divisors. It's not a collection of homology classes. They are actual curves. That all, I'm always, so sigma is really, some very specific curves. So sigma 1 up to sigma n, that are fixed in your submanifold. So it's not just their classes, it's the curves themselves that are given. Okay. And I look at all those diffeomorphisms, preserving some homology class of the blow-up form, and acting and sending each of these individual exceptional divisors to themselves. Okay. And I look at the space of all cohomologous forms for which these submanifolds are symplectic, and then a relative version of Moser lemma shows that you still have a very nice vibration here. And what is the fiber? Well, the fiber is precisely the set of symplectomorphisms that act by sending each of these exceptional divisors to themselves. Okay, so what you recover is the full stabilizer when you look at the action of simp on the embedding spaces that I wrote before. So this is precisely the stabilizer. This is homotopy equivalent to the stabilizer of my collection of n balls. When I look at the action of simp on the embedding space. So this other vibration gives me the right stabilizer. So if I can investigate the homotopy type of this stabilizer from this vibration, then I will learn something about the embedding space.
This is an homotopy vibration.
Huh?
It's an homotopy vibration.
This one?
Yeah.
No, it's the exact fiber.
Yeah, okay.
Yeah, it's a no. We are going to the homotopy fiber next slide. Okay, so yeah, so this is the homotopy fiber. Okay, so now instead of working on action of diff on symplectic form, which is very bad because we don't know diff, we don't know the space of symplectic forms in general. Okay, so what we will do is that's a beautiful idea due to do that. We'll switch actually. We look at space of pairs, omega prime comma j, where omega prime is one of those forms cohomologous to the form I'm interested in, and making my exceptional divisor symplectic. And j is compatible with omega prime. So we look at pairs like this. And what happens is that this space, I have my space of pairs there, and then I have two projections. Of course, I project to, say, the first component or to the second component. And it turns out that these are vibrations with contractible fibers. So this means actually that these projections are weak homotopy equivalences, both of them. And what you get from this is that your space of symplectic forms, the relative version of it, is homotopy equivalent or weakly homotopy equivalent to a space of almost complex structure. This space of almost complex structure, script A sub C, is by definition this set of all J's compatible with at least one omega prime in this set. And you can actually make a substitution now. If you are only interested in, say, homotopy considerations, then you can make a substitution, although diff does not act transitively on space of J's, simply because, for instance, you have non-integrable J's, and you cannot map them to integrable ones, and it's very far from being, very far from being a transitive action. Well, it turns out that the homotopy fiber of this map is still homotopy equivalent to the stabilizer of n balls that we are interested in. And this in particular induces a long exact sequence in the homotopy group. So what is nice now with this new vibration is that as C varies, remember that one thing we would like to understand is how, for instance, the embedding space depends on the capacity. So as C varies, well, this space, of course, does not vary much, because it only varies if the cohomology class here becomes very kind of quite exceptional. Okay. But for a generic choice of C, then actually this will not vary for small perturbations of capacities. And and then you can investigate what happens when you start changing the capacities. And what is more important is that because this is the homotopy fiber, because this homotopy fiber is also the stabilizer of my original vibration, then you know that the homotopy type actually of this stabilizer only changes when the homotopy type of this map, this action of diff on script A changes. And this is what we will be investigating now. So we say that two set of capacities, 0, C1. So I always consider the same number of balls, N. Two set of capacities are in the same stability component if the corresponding embedding spaces have the same homotopy type. And yes, and more of this. So I want to be able to find a deformation of these numbers, a continuous deformation, so that the homotopy type is constant along this deformation. So it's really a path component within all possible set of capacities. And the stability components then will be determined by the previous vibration by investigating this evaluation map, how diff acts essentially on the space curly A of symplectic forms. Of almost complex structures. And so our goal again is to compare what happens with the script A for different capacities. And now this is the entire idea why we switch to a space of almost complex structures instead of a space of symplectic structures. It's because now we can play with what is called the inflation procedure, but a very specific version of it. So the J compatible inflation in a weak form, a strong form is not known to hold. Okay, but well, that would be another talk actually. But so the thing is that we can use inflation along a J holomorphic submanifold to change the cohomology class of a form in the direction which is the Poincaré dual to the submanifold, keeping J compatible. Actually, this is not quite true. This is not quite true. So there was a mistake discovered a long time ago by some student. Actually, there was a mistake in the exposition, and it is true on the nose if the self-intersection of the manifold Z is non-positive. But for positive self-intersection, actually, there is a problem. I think we have a solution to that. So complicated that I'm not even sure it's a solution. In any case, there's a weaker form. So instead of asking that the form that you get by inflating is itself compatible with some symplectic form, you are allowing to find another symplectic form in the same cohomology class. Yes.
Normalement, c'est 1 heure la dernière à expliquer l'emploi de l'unité.
Ah, ben,
Donc, ben, tu peux prendre 5 ou 10.
oh, no.
Right.
So I just learned that I cut by half an hour.
No, it's in the department.
Okay, no,
All
but
talks in the afternoon or 1 hour.
really?
All talks in the afternoon.
I'm very bad with watches and calendars. So, okay, so stability chambers. Let me just speed up a little bit. I'm sorry about this. I was sure I had still half an hour. Okay, so okay. So the idea is this. So you have one set A for some capacity C. You have another set script A for some other capacity. And what you want to show is that you want to show inclusion of one into the other. So we are comparing these sets, but we will actually be showing the following thing. Under suitable choices or under suitable conditions on these two different set of capacities, not only we have a map, but we have actually a very natural map, which is an inclusion on the nose between these two sets. As long as you can take any j here, find a z that is geomorphic here, and then perform the inflation so that you change the cohomology class of your corresponding to your blow up to the other one. So actually, the only obstruction to finding curves here that realize this inflation are the existence of negative curves that will eventually prevent you from inflating, because these negative curves will have areas that will be decreasing, and if eventually, because if you assume that J remains, compatible with your form, all these things must be symplectic, so they cannot have negative area. So eventually, you will find that the only obstruction for say inclusions like this come from specific negative curves whose area are decreasing along all the possible inflations that would bring C to C prime. So eventually you are forced to make some curves negative, some symplectic curve negative, which is not possible. So this shows actually that this cannot be realized. On the other hand, you prove that if you don't have any of these negative curves, then you do have some manifolds so that you can perform this thing. So they are really the only obstruction for the inflation process that shows that one script A may be contained in some other script A. And this is essentially what summarized the content of this slide. The relevant curve you have to understand in order to understand which script A are included in which other script A are all those negative intersections embedded spheres, symplectic sphere that are embedded of a negative self-intersection. And the one that will bring obstructions are the one for which the self-intersection is less or equal than -2. And the nice thing is that if I go back to CP2 now and I apply all these ideas and I look at a set of not more than 8 balls in CP2, then the nice thing is that we can list all those bad curves that create obstructions to the inflation process. And because we can list all of them, we can tell which C, for which capacity C, I have the exact equality between the two C and C prime. I have equality between script A, C and script A, C prime. So here are the relevant curves, not very surprising. Now, the thing is, remember that in all this story, I have a fixed set of exceptional divisor that must be symplectic and geomorphic at all time. And this actually prevents most of the bad guys to appear. By positivity of intersection, because I force these exceptional divisors to be there, the only negative curves on CP2 that can appear and contribute to, say, obstructions are the ones that are essentially coming from blowing up points along lines. And this corresponds to genericity conditions for points on CP2. And because of this, the conjecture is that the embedding space has the same structure as the configuration space of endpoints. Okay, but this is for small balls. And as the balls are increasing in size, so suppose you have a line. So if you have a bunch of small balls, you can all fit them on a line. So it means essentially that there will be, so if this is the ball 1, 2, 3, 4, if they are small, this means that such a configuration of ball is possible. And what happens is that when you blow up, what you get is a curve in the class, say, in this class here, which is one of those obstructions. Okay, but if the sizes become too large, maybe this one, cannot fit anymore on a single line, because the area of L is finite, is set to 1, say by convention. And then if the size of the capacities here sum up to something bigger than 1, then actually I can no longer blow up such a configuration, and I will not have any curve in this class. So it means actually that the space of embedding is essentially obtained. First, you have the configuration space, the full configuration space. This is for small balls. And as the ball grow in size, then you start losing strata corresponding to genericity conditions on CP2. And eventually you will get something that has actually no negative curve if all the balls are very sufficiently big. Okay, so essentially what happens, and we are able to prove it, say, for up to 4 balls completely. And I have one student, C1, who is investigating the case of 5 balls, which should work also with current technology without improving any known result. But starting with 6 balls, this correspondence between embedding spaces and configuration of points, I think is still true, but we cannot use current technology. We have to improve on current results to be able to prove it. And so, which is quite tricky, but I still believe that it is working. So I'm very. Can I take 3 minutes?
Just 2, yeah.
So
The 1.5.
So anyways, I had a few slides explaining exactly what happens, but I just want to state one thing at the end. Okay, so why we expect all this to be true to some extent is because when we look at, from a topological point of view, when we look at the moduli space of endpoints on CP2, which is the set of all points modulo complex automorphisms, you want to understand this from a topological point of view. You want to be able to compute the, say, rational cohomology of this. Okay, so what you do first in homotopy theory, you will replace this by, say, what is called the homotopy orbit or the Borel construction relative to this action. Okay, so that you get a good topological quotient. Okay. Now, in the case of CP2, there is a remarkable result of Gromov saying that the symplectomorphism group CP2 is nothing else than PU3, which is homotopy equivalent in a natural way to PGL3C, which is the automorphism group of CP2. And if you want to look at the evaluation map here, how PGL3 acts on configuration of endpoints, from an homotopy point of view, you are only interested in really computing the homotopy fiber of whatever this map is. And it turns out that from Gromov results, that when you replace this map by a cofibrant replacement here, you make this in order to compute the homotopy fiber. A natural choice for replacing PGL3C is precisely by replacing by SIMP. So essentially, when we look at how SIMP acts on configuration spaces, here we are essentially understanding the homotopy fiber of this map here. So we are essentially doing the first step in the understanding of the configuration of the moduli space of points on CP2. And I don't have time, but this brings into consideration all the Dunning-Mumford compactification related to these moduli spaces. And again, I have students working on this. I would have been very pleased to talk about this in the next half hour. But I have to stop.
Okay, so I suggest that we just ask questions personally to the speaker, for those who wish to stay a few more minutes. Okay, so thank you very much, Martin.
Martin?
Time for questions.
Martin?
We should thank the organizer. Thank you for this.
Martin?
Johan. And Stephen, of course.
Can I just add one sentence? Okay, so I just want to say that everything that I discussed is basically already on a preprint on archive. Unfortunately, this preprint contains many mistakes. I mean, typos and so on. And we are going through a second version that will be
So it's a preprint, it's a misprint.
it's not a preprint, it's a misprint. All the results are still exactly the same, but there are several places where we found funny mistakes.
Martin?
Yes.
Yeah, here in Zoom.
Yeah, I'm listening.
Yeah, so I think the counterexample to Groma Varu that was pointed out, the word that was missing in